glucose. Fructose has the same one. And so we're going to have to balance that out. So 6, 6, and 6. And then the glucose is just 1. But this is a synthesis type of reaction. We're taking two things and we're going to combine them, right, to make two totally different things. We're going to make the glucose molecule. So that's a type of a synthesis reaction or a combination reaction. And everything is going to combine in simple whole number ratios. A decomposition is the opposite, right, of a combination or the opposite of a synthesis reaction. So a nice example of a decomposition would be, so this is another bodily function for us. This is going to be hydrogen peroxide, so H2O2, and it's in the aqueous phase. So this is going to decompose, and what you notice about a decomposition reaction is that typically you have one thing on the reactant side and then more than one thing on the product side. Hydrogen peroxide is a byproduct of respiration. It's also lethal to us. It's a toxic species, and so we have enzymes that allow us to break this molecule down quickly, so quicker than the time it would take to kill us. So we actually make this toxic molecule in our bodies, and we have an enzyme that allows us to break this down into water and into oxygen gas, which is really not difficult for us to deal with, right? So we're going to balance that. So that is a decomposition reaction. You have one molecule on the left, and it is decomposing to form two molecules on the right. A single replacement reaction is, and actually some of these reactions fit a bunch of different categories. So for example, this single replacement reaction is something that you might do in the copper lab. I think you guys use magnesium, but I'm going to go ahead and change things up and just use zinc just to keep it fun. And this salt is going to be dissolved in water. So if you were doing the copper reaction, this copper 2 sulfate looks like windshield washer fluid, actually. It's a pale sort of aqua color. Well, pale depending on how concentrated it is. And we have some solid zinc. And I'm going to, so you'd typically draw these reaction arrows going in both directions. But we're just going to go ahead with our synthesis arrows, or our like heading from reactant to product arrows, just to focus on the reaction types, and we'll save the redox stuff for another time. So what ends up happening in part of the reaction that you're interested in is that we're actually going to precipitate the copper as a solid so that you can recuperate it, right? You want to recycle your copper chunk. And so then what you get is zinc sulfate. And the cool thing about this is that's also soluble in water, so it's aqueous. So you're going to take solid zinc and add it to what looks like a beaker of windshield washer fluid, but it's copper 2+ and then sulfate, which is 2-, right? And that has that pale aqua color. But zinc sulfate, which is zinc 2+ and the sulfate 2-, that is colorless. The zinc should then look like it's dissolving, but it's actually not. It's oxidizing. And then the copper is like this sort of rust-colored solid that's going to precipitate. So this is a single replacement reaction where you're going to replace the copper with the zinc. It's also a redox reaction, so we're transferring electrons from the zinc to the copper, and it's also a precipitation reaction, so you are going to be precipitating solid copper. So this one fits a bunch of different descriptions. A double displacement or a double replacement reaction, I can take some potassium hydroxide, so KOH, and that's going to be soluble. And I'm going to allow it to swim around with a solution of lead 2 nitrate. All nitrates are going to be soluble in water at room temperature. And so over on the other side, we're going to do sort of like a double displacement. So this is like square dancing, where we're going to switch off partners here. So I have the potassium, which was hanging out with the hydroxide, is now going to hang out with the nitrate. And that'll be aqueous. And I'm going to make lead 2 hydroxide. How do I know it's lead 2 hydroxide? In other words, how do I know that I need 2 hydroxides? Because hydroxide always has a -1 charge. And if I had lead 2 nitrate, then I have the lead 2 plus ion. So I need to balance that out with 2 hydroxides. So I'm looking from left to right here, and I notice that my reaction is not balanced. On the reactant side, I have 1 hydroxide anion, and on the product side, I have 2. So I'm going to put a 2 in front of the potassium hydroxide, but then I've messed up the number of potassium moles, right? So I come over here and I put a 2 in front of potassium nitrate. And that works out because I needed 2 nitrates to balance out the lead 2 plus. So now everybody's balanced. Something else you might want to notice here is not just that we did a double replacement reaction, but we also, this is a precipitation reaction. And a precipitation reaction is where I'm going to take my reactants and I'm going to combine them. And on the product side, one of my products is not going to be soluble. And you see that little lead 2 hydroxide? That is not soluble in water. And so that is going to crash out, or in other words, it's going to precipitate from solution. So in chapter 8, we go through solubility rules, and that will be one of the things that you'll have to predict after going through chapter 8. Right now in chapter 7, we're just talking about a double replacement reaction and a precipitation reaction. It's just reaction types. Moving forward, it'll be your job to notice that lead 2 nitrate is soluble in water, but lead 2 hydroxide is not. And we'll cross that bridge when we get to it. So we've already done a bunch of redox reactions, and we call them redox reactions because you can't have the oxidation without the reduction, and you can't have the reduction without the oxidation. So an oxidation reaction, which is covered in chapter 8, is where you're going to steal electrons from somebody. But who's stealing the electrons, right? So when you get oxidized, you lose electrons. When you get reduced, you gain electrons. So the species that stole the electrons, right, or in other words, the species that had a stronger pull on the electrons in the pot, is going to get them and become reduced. When that happens, the something that got robbed gets oxidized. So this is a little combo pack, and we usually call these redox reactions. And we've already done a bunch of examples, but I can toss a simple one up there. Redox reactions are pretty easy to see when we have charges to deal with. So let's just take some silver ions, and if they're charged in water, they'll be floating around, right? So aqueous, and then some solid aluminum. And we're going to move this over. We are going to oxidize the silver, or I'm sorry, we're going to reduce the silver, we're going to oxidize the aluminum. And when we reduce the silver, it gains an electron, right? A single electron, so it'll be solid. And we're going to oxidize the aluminum to its typical oxidation state, in this case, +3, right? And so now, is it possible that you can have aluminum +1? Anything's possible, but the most common oxidation state for aluminum is +3. And I thought it would be nice to show this example because look at how, first of all, when you have an ion, it's going to be aqueous. When you have a metal that has all of its electrons and nobody else's, the oxidation state is 0. It's solid, right, in water. And so if we're going to transfer electrons to silver one at a time to make silver 0, but we end up with aluminum +3, then we're going to have to use 3 silver ions and create 3 moles of solid silver on the other side. Now all of a sudden I have not only balanced the species, but I've also balanced the charge. So we're just bringing balancing reactions back into this. This is an example of a redox reaction. Why? Because the silver has gained electrons, so this gets reduced, and the aluminum is going to lose electrons. This gets oxidized. So I went from silver with some missing electrons, or I've got 3 moles of silver ions, silver plus 1. So each one of those ions, right, missing 1 electron. But I look at the aluminum that went from aluminum 0 to aluminum positive 3. 3 electrons were lost. They didn't just evaporate into the universe, right? They went to the silver. So I had to balance out the species and the charge. So a redox reaction is something gets reduced, something gains electrons, and the thing that it gains electrons from is the thing that lost the electrons. Does that make sense? And so that thing got oxidized. Call it a redox reaction because these things happen at the same time in the same pot. In Chem 32, you'll get down and dirty with redox reactions. So for now, we'll just leave it at that, the type of reaction that it is.